Did you know that Marie Curie, one of the pioneers in the study of radioactivity, is actually believed to have died in 1934 due to radiation exposure? Hi, welcome to Physics is Easy with Mr. Jesse. This tutorial is on Chapter 29, Section 6, Nuclear Reactions. For this lesson, we are going to calculate the energy required to balance the equation of a nuclear reaction, differentiate between endothermic and exothermic reactions, and calculate the threshold energy of a nuclear reaction. Before we go into the lesson proper, I would like to express the units for mass that we are going to use for this lesson. Now, it is convenient to use the unified mass unit U to express mass, and this is based on the definition that the mass of one atom of carbon-12 is exactly 12 unified mass units. Now, here is the conversion factor. One unified mass unit is equal to 1.66 times 10 to the power of negative 27 kilograms. Also, mass can be expressed in mega electron volt, and that is one unified mass unit is equal to 931.494 mega electron volt, and this is actually based on Einstein's famous equation E is equal to mc squared, which we are going to talk about when we would reach a theory of relativity. So here is an equation that will allow us to apply the conversion of mass to energy. The problem reads, we show that radium-226 nucleus undergoes alpha decay to radon-222. Calculate the amount of energy liberated in this decay. Take the mass of radium-226 to be 226.02540 unified mass unit, and we also have the unified mass unit of radon-222 and the unified mass unit of the alpha particle. So first we have to write the alpha decay equation of radium-226. So we have radium-226, we have the atomic number 88. As it undergoes alpha decay, it would lose 2 neutrons and 2 protons, so we will have 222, and we have 86 here. This is radon plus the alpha particle, which is denoted as a helium particle or helium atom. Alright, so to begin with, we actually have to convert the change in mass into energy, and the change in mass is equal to mass final minus mass initial. And the mass final is just equal to the mass of radium-222 plus the mass of the alpha particle subtracted by the initial mass, which is the mass of radium-226. And we will have to substitute the values as what's given in the problem, and this would eventually give us 0.005229 unified mass unit, and the negative sign here indicates that the energy has been liberated if we are going to equate or relate mass with energy. So since the change in mass is negative, therefore energy is released or liberated. Now, to convert this mass into energy, we will just have to multiply with the conversion factor that in every unified mass unit we have 931.494 mega electron volt, and therefore the energy that is liberated in this decay is 4.871 mega electron volt. Now, when we talk about nuclear reactions, The structure of a nuclei can be changed by bombarding them with energetic particles, and these changes are called nuclear reactions. Now, similar to nuclear decays, the atomic numbers and the mass numbers must balance on both sides of the equation, so they are quite related to the radioactive decay. Again, the atomic numbers and the mass numbers must be the same on both sides of the nuclear equation. So here is an example of a nuclear reaction. An alpha particle colliding with nitrogen. This is our alpha particle, and it collides with nitrogen to produce an atom, X, and a proton. So this one here is our proton. Balancing the equation would allow us to determine what X is, and we will have X must have a mass number of 17 and an atomic number of 18, and therefore X is actually oxygen 17, knowing that the element which has an atomic number of 8 is oxygen, and we will have to use our periodic table to deal with such a problem. So the reaction then is the alpha particle colliding or being bombarded to a nitrogen atom will give us an oxygen atom and a proton. And if we're going to check on the mass number, so that would be 4 plus 14, that is equal to 18, and it is also the same on the right side of the equation. 17 plus 1, that is also 18. And also the atomic numbers on the left side of the equation should be equal to the atomic numbers on the right side of the equation, and in this case we have 9 on the left side and 9 on the right side. So this is a balanced nuclear reaction equation. Now, similar to the familiar chemical reaction, nuclear reactions can also be exothermic or endothermic. Now, in an exothermic reaction, there is mass loss. That means that the final mass is less than the initial mass of the atom. And this is because the mass has been converted into energy, so there is a release in energy. That means our Q value is positive. Now, Q value is something that I will be discussing on the next slide. We will be looking more into Q value on the next slide. Moving on, in an endothermic reaction, there is mass gain, so therefore the final mass of whatever the atom that is produced is greater than the initial atom or the initial mass of the atom, and energy is needed in the form of kinetic energy of the incoming particles. Again, I will be discussing more about these two on the next slide, and therefore the Q value in an endothermic reaction is negative. In accordance with the law of conservation of energy, energy must also be conserved in nuclear reactions, and the energy required to balance a nuclear reaction is called the Q value of the reaction. Now, to see the importance or the meaning of Q value, consider this equation that I introduced earlier. So we have the helium particle colliding with the nitrogen atom, and in the process producing an oxygen atom with a proton. Now, before the reaction, the total mass is the sum of the masses of the alpha particle and the nitrogen nucleus, so these masses here, and that is equal to 18.005676 unified mass unit. Now, after the reaction, the total mass is the sum of the masses of the oxygen nucleus and the proton. So the sum of the mass of the oxygen nucleus and that of the proton, and that is equal to 18.006958 unified mass unit. Now, if you're going to look at these values, the total mass after the reaction is greater than the total mass before the reaction. and the difference is 0.001282 unified mass unit, and we call this difference as the mass deficit. Now, if we multiply this mass deficit by the conversion factor 931.494 mega electron volt per unified mass unit, we will have 1.14 or 1.194 mega electron volt, and this is what we call as the energy deficit. And now this deficit is expressed by the negative Q value of the reaction. So this is our Q value here, and it has a negative value. Now, reactions with negative Q values are considered to be endothermic. So again, the Q value is negative. So Q value negative, we will have an endothermic reaction. Now, such reactions won't take place unless the incoming particle has at least enough energy to overcome the energy deficit. In relation to the previous slide, in order for an endothermic nuclear reaction to occur, the incoming particles must have a minimum amount of kinetic energy called the threshold energy. So this energy must be enough to overcome the energy deficit. Now, threshold energy, or Ke minimum, may be computed as 1 plus the mass of the incident particle divided by the mass of the target particle multiplied by the absolute value of the Q value. Now, our incident particle here, it could be alpha particle, it could be an electron, and our target particle is the atom. So it could be any type of atom that would undergo the nuclear reaction. Remember that if the amount of energy of the incoming particle is less than the required amount, or the threshold energy, the reaction cannot occur. So let's look at our previous equation and solve for the threshold energy for this particular nuclear equation. So we have the equation Ke minimum, or the threshold energy, is equal to the quantity of 1 plus the mass of the incident particle divided by the mass of the target atom multiplied by the absolute value of the Q value. So let's substitute the values that we have. Then our Ke minimum is equal to 1 plus the mass of the incident particle, or the alpha particle in this case, is 4.002602 divided by the mass of the target particle, which is the nitrogen atom, and that is 14.003074, multiplied by the Q value that which has been obtained earlier, and that's negative 1.194 mega electron volt. Again, the negative sign here tells us that there's a deficit, and therefore this is an endothermic nuclear reaction. So manipulating these quantities here would lead us to the threshold energy, and that is equal to 1.535 mega electron volt. Now this means that the nuclear reaction shown above will not occur if the incoming alpha particles has a kinetic energy less than 1.535 mega electron volt. However, if the kinetic energy is equal to or greater than 1.535 mega electron volt, then this nuclear reaction will happen. At this point, I need you to log into WebAssign and do the task entitled Nuclear Reactions. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.